Welcome back student to our Mathematical Methods 1 course, where we are now learning about the function space and something called orthogonal functions. So, if you remember in our last class, we have suppose a set of function like this. Now, also we define something called inner product. If there continuous set of function in the interval a and b, then phi I phi j defined by this notation, which is a to b phi I star x phi j x dx is equal to 0. If this is 0, this is the inner product of these two functions, ith and jth function. If it is 0, then the set of functions are called, this suggests me that it is orthogonal set of functions. They are orthogonal set of functions. Now, apart from that, if they have this property also, now I am taking the same function, same two function with inner product, and then in the right hand side, according to the definition, if this quantity, normally we define this quantity as a norm of the function, if this is 1, then we call these functions as normalized. Now, if both the conditions are applied together, if they are orthogonal set of functions and also they are normalized, then we can write in a single line, instead of 0, by the way, it is 0 when I is not equal to j. This is 0 when I is not equal to j with this notation. Now, I slightly change this thing because they are now normalized. So, I should write as delta ij. If I write this is as delta ij, that means when I is equal to j, then it is 1, and if it is not equal to I not equal to j, then it is 0. So, then we call this as orthonormal functions. Fine. So, now we have a set of functions with considering that they are orthonormal, then I can write any function fz fx in terms of this function like this. But you should remember here in the function space that the dimension is infinity. So, I should not stop here, it should go with infinity. So, that means this set is in principle is infinity. So, now I can represent a particular function in terms of this phi 1, phi 2 and these things, where the relationship between phi n the relationship between phi's are this, if they are orthonormal then. So, now I can correlate these things with my vector notation. Any vector, for example, x can be represented like this, c1 e1 plus c2 e2 and cn en If it is a finite dimension, then it is okay, but there is a possibility that vector can be infinite dimension, then n tends to infinity, then I can write these things and these things will go on. I mean, I can write more terms. But the thing is that now these and these are correlated to each other. If you try to find out that a function can be represented, a vector can be represented with the basis, here a function can be represented with some functions, other functions which can behave like a basis. So here this can behave like a basis, that is the first thing. Last we mentioned that. So these are a special function which can work as a basis, this one. Now if they are a basis, then they are need to follow. For example, in function in vector space, if I write somewhere here in the right hand side, say ei ej, inner product of these two is delta ij. That is also true for here in this case. So here we have the similar kind of thing, phi I phi j is delta ij. But apart from that, there are another important property in vector space, which is this. If you remember, we also derived these things and we called it as completeness or completeness. The basis should follow these things to completely expand a function in terms of this basis. If I say ei, e2, e3 are the basis. So this is the completeness. Now the question is, what is the counterpart of this completeness in terms of this phi 1, phi 2, phi 3. So I know that this is okay. Inner product and this inner product both are by definition they are different, but they are correlated to each other. But what should be the correlation of these things in function space, that we try to figure out, which is interesting and which is important. So in order to do that, we need to first know what is delta function. So let me first write something called Kronecker delta, defined as delta ij. So this is the property of this delta ij is that this is equal to 0 when I is not equal to j and equal to 1 when I is equal to j, something like delta ij, but Kronecker. So what is the significance of these things? Suppose we have a sequence of quantities, say a1, a2, a3, an and so on, a sequence of numbers we have. Now if I want to choose a particular element, say aj, from this, I can do one operation, and this operation is I can make this quantity over I. So I can multiply this quantity with the varying. So here I is the dam index which is running. So taking different value, I am getting in the right hand side I am getting different quantities. But please note that this delta function has a property that when I is equal to j, only then this become 1, other case it will going to vanish. So what happened that this will going to extract this aj when I equal to j, then this quantity become 1, this I become j, then eventually I am getting this quantity back. So I can extract these through this by using Kronecker delta. Now for the function, which is this very brief idea of these things, I can do the same thing for function, which is called the delta function. So suppose this is my delta function, you know about these things. The property is this quantity is 0 when x is not equal to x prime. X is varying parameter, it is sliding, and when this value is equal to x prime, then this value is not equal to x prime. All the value of x which is not equal to x prime is 0 and equal to infinity or tends to infinity when x is equal to x prime. Not only that, if I take integration of this function, so I will have say some interval a to b where this function is defined, I should have the value 1 here. So, this is the property of a delta function. Now, with this knowledge of delta function, I believe all of you have some idea about the delta function. So, I am not going to be very detailed about this delta function and all these things. Rather, I try to use this delta function to find out how this completeness is related to that quantity. Suppose we have a function in the interval say a to b. This is my function of x which is distributed over that, and a particular point is x equal to x prime. This is a prime. So, exactly like the way Kronecker delta is used, I can use delta function here to find out the value of the function as at x prime with the same logic. So, what I will do that I will multiply this quantity over x and integrate, because this is a continuous function, there is no discrete quantity there, we need to make a summation over that. So, here in place of summation I need to put the integration, because this is a continuous things a to b, and when I am doing that, then what I am doing that I am sliding this delta function over that, x is changing, this is also changing, because this is a behave like a dummy indices. If you correlate that to the previous notation which is given in terms of summation sign, here what happened that it will slide. When it will slide, what happened, it will take only one value when x is not equal to x is equal to x prime. In that case I will have this quantity in my hand. So, this is the beautiful property of the delta function which is correlated with the function f x. With this I will get this. So, I can write it in a different way. I can write my f x can be represented like something like this there. Okay, up to this is fine. So, I know how to extract a particular value of f x at x prime with the use of delta function, with the property of the delta function. Now, I know f x can be represented completely. If I able to represent this completely, then I can write it as C I phi I x sum over I. So, I can write the function in terms of basis function. So, now this is a basis function and this quantity is the corresponding coefficient, exactly like write a vector. The way I write a vector, here I am writing the same thing that I described. So, this is a basis function, say basis, and I can write it in this way. If I write in this way, then I can calculate C I by using this. How? So, I can say I can write this as this way, say C1 phi 1 x plus C2 phi 2 x phi n x, so on. In the left hand side I have f x in my hand. Okay. So, what I will do, I will make a inner product both the side with respect to say phi I. So, if I do that, then if I make inner product with phi I, so left hand side will remain this, and then the right hand side I should write something like this: phi I phi 1 plus C 2 phi I phi 2 C I phi I phi I and C n phi I phi n and so on. But the interesting thing is this quantity, this quantity, this quantity, whatever the quantity we have with I and these things. So, it eventually gives one thing, that since the functions are orthogonal to each other, this gives you 0. So, I know this is true here. So, that means in the right hand side I will only have C I like this, okay, C I. So, if I expand these things, so what is the definition of the inner product? So, this side I can write as A to B phi I x prime. I need to put a star here. If this function is in general a complex function, then and then f x prime dx prime. This is in the left hand side, which is equal to C I, because left hand side is the inner product and I know what is the definition of the inner product. I just use the definition of the inner product for the function in the limit a to b for which the function is defined, and I can extract what is my C I here with this. So, now I know what is my C I. So, I will replace this. Mind it, when I calculate the C I, I integrate over this thing with the prime, because this is the Dam index. So, whatever I like I can do. So, there is no problem by taking this as a prime, because this is nothing but a number. So, eventually I have f x is equal to sum over I C I. I should write the complete form A to B phi I star x prime, then f of x prime, then dx prime, bracket close. C I represented in this form and then multiplied by phi I x, which was already there, Now, in the next step I just change this integral sign, take it outside, say a to b, I write it in this way, a to b. In the bracket I put this summation sign inside, which is over I. I write two quantity phi I star x, then phi I x, because this is over I. So, I take all the I term together and I will get these things, bracket close, then f of x prime dx prime. Here I should write it prime here, okay. That time I mistake. This is my outcome. So, now if I compare, say this is my equation 2 and this is my equation 1, that I have already figured out. If I compare these and these two, then I have a relationship between delta function and my basis function. The rest of the things are same. So, this quantity is equal to this quantity. If I write these things here, so basis functions, if they are complete, okay, now I put a prime here, I missed that. This quantity is equal to delta of x minus x prime. So, this is the counterpart, whatever the thing we have in vector space by using the vector, this completeness, I can get the similar kind of thing here for the completeness, and this is the counterpart. So, I should write that like here I have the inner product thing, I should also have a completeness here, and this case the complete, in the case of function the completeness should be represented by this phi I x star phi I x should be equal to delta x minus x prime. This is the same thing as this, we called it as completeness. That means, if I want to find out the basis functions which is in general infinity, then the thing is that this basis function should follow this orthonormal property, that is for sure. And also for completeness, if I want to describe a function or write a function completely, then this completeness is also should be, the basis function should also follow this completeness nature or this completeness property. So, with that we have an idea about the basis function, and this basis function should follow this completeness things, fine. Now, we will define a function in terms of this basis function. So, now the same thing I can write this as Ci, this, a function can be represented completely in terms of this. Now, how can I find Ci? I have already shown. So, if I do the same thing, for example, here phi I, the functions, set of functions is orthogonal, just orthogonal. I am not saying that this is normalized, this is orthogonal. That means they follow this rule. I can write this function in this way also. When this is 1, then it is delta ij. If these things are not normalized, then when I equal to j, I will have mod of these things, I or j, whatever. Okay. So, this is the mod of this function. So, I write it in this way. So, from here I can find out the Ci exactly the same way just a few minutes ago I did. So, I can readily figure that my Ci should be, if I integrate over, if I make a okay, let me do it in this way. I use phi k, another kth function, I impose this phi k over f to make a inner product, and in the right hand side what you will expect, you will expect that I will basically make the inner product a to b summation of I Ci phi I x multiplied by phi k x dx. So, now this quantity, if I do the integration, I know that this is this quantity. So, readily I can understand that it will be just I Ci delta I k mod of phi I square, because if I take the summations and outside and integrate it over this quantity become this. By the way, I am not taking the star here because assuming this is a real quantity, but even if it is not a real quantity, if it is complex, then there is the procedure is exactly same, no problem with that. Even if I take star or not star, you will not going to change anything, these things. So now if I do that here, then what I will get is basically delta ik mod of phi I square, that already I wrote here. So I just put this here, and now if I take the integration, if I take the summation and this over I, then when this I is equal to k, then I will have something ck phi k star. So from here I can find this coefficient ck. So ck is phi k f divided by phi k star. Not a very new result, I must say, but important thing is that you can write this entire function in this way. When this has a property of orthogonality, if this function has a property of orthogonality, then you can find out what is the coefficient associated with that. Exactly the same way you can find the coefficient in the vector space, you can also find the coefficient here, and this coefficient is normally called the Fourier coefficient. Fourier coefficient. Now why this coefficient is look like this, we can do maybe in the next class, that if I take this function is equal to this function, if I say this, now I know that I need to define these functions, I need to decompose this function in terms of basis function, and basis function is of infinite dimension. That means I need to go the infinite distance or infinite number of points I need to take. So if I take the infinite number, then this value will be gradually equal to whatever the function is giving to you. But if I don't take the infinite number of basis function, then what happens, right hand side will be nearly equal to this or of the order of this, but not equal to the same quantity. So now in order to calculate the coefficient, I can calculate the coefficient in this form, this particular form, if they are orthogonal, if these bases are orthogonal. In the like a vector space, it is not necessarily that the function can be represented in terms of only the orthogonal bases. Any linearly independent set of bases can be used, any linearly independent set of functions can be used as a basis like in the vector space, but I have some additional advantage over that. This additional advantage is that if I write the function in terms of orthogonal bases, I have the minimum error. So with that point I like to stop. In the next class I will start from here and show that how the minimum, because I want to have a minimum error, and if you have a minimum error, then you will automatically find, naturally you find that your ck will be this quantity. So with that note, let us stop the class here. So in the next class we start with this Fourier coefficient stuff and try to find out what is the condition to have the minimum minimum error. When you find the minimum error, then naturally it will come that my coefficient should be like this only. So with this note, let us conclude here. See you in the next class. Thank you.